Okay. Thank you, Sylvia, and thank all of you being here. So, given that nearly half of the presentation in these mini symposiums are from our group, allow me to present briefly our background. So the history starts inside the chapel. All of these chapels are in Barcelona, where we come from. And in particular, in this old chapel, we hosted Mare Nostrum 4, which in fact, rest in peace. But going up, this is our center, recently building center in the next to that chapel. So this is Barcelona Computing Center. And recently we installed the new machine, Mare Nostrum 5. So we belong to this team in one of the departments of the center, and we develop, all of us, the same multiphysics couplet problems based on finite element method, and of course in HPC environment. But our specific research group, it's focused on biomedicine applications. So we aim to simulate the human body, which is the most complex and challenging problem we can imagine. And the results of combining the ALIA team or ALIA code with the human body complex problems is ALIA Red, which integrate all the simulation tools for biomedical research. So as in fact Phoebe was presenting, these are the large scales and organization from the molecules to the main body. And in biological systems, very low levels decisively influences high levels, but we need to cut our domain. We are focused on this organ level, so we need to model and define properly the boundary conditions that we are not considering. And this is mainly our work in our daily research. These are the phases for all of our established group. And let me go through the topic of today of this talk, which is respiratory systems. So we have been working in different projects addressing different questions of this so exciting organ. And the talk that I'm going to present right now is focusing on this distal part of the lungs, the alveoli. But in general, for all these projects, what we, in a more engineering point of view, what we do is of course, solving the equation with all the physics and mathematical important aspects, couple them if it's needed, but consider an important and most crucial point based on my point of view, which represent the patient-specific anatomy and physiology. But of course, we need to analyze properly the results, considering the question of on hands, and a non-trivial question for biomedicine application in general. This is not so equivalent for the engineering point of view. We don't have any tunnel wine to validate properly our results, but we need to address all the workflow. So let's go with the alveolar sacs. This is the smallest functional respiratory unit, which is a large surface in the lung. And in fact, it's a quite unknown structure. These are the most detailed images obtained so far. And so let's go with our comparison. And these are the 4 geometries that we have been working with. So we have the geometry 1, the most simple and synthetic geometric alveolar sac. We also create this other more complex as a step forward, which comes from the typical image on the bibliography medicine. and where we have some, as you could see, not so simple with bifurcation and connections between different tracks. Geometry 3 is based on these microscopical images, and in fact is the same methodology that we apply for creating the geometry 4, which is enlarged geometry 3 version to fit better with the proper anatomical volumes. In fact, we checked in the literature that this structure, geometry 4, is equivalent to 8 parts of a real acinus structure that we have in our real lungs. And we enlarge and create this geometry 4 once we have confident with our resulting mesh, because it's a novelty mesh. You don't have any similar geometry simulated with CFD techniques to simulate the lungs. So we check in the literature with this paper, Application of Machine Learning for Segmentation of the Pulmonary Acinus Image by Synchrotron X-ray tomography, that the image that we saw in the paper was well, we have great and nice similarities with our geometry. And in fact, let me share with you our reference. So this geometry 4 and geometry 3 for us are like a sponge. So geometry 3 is big, also Bob, the Bob sponge, and geometry 4 is Big Bob, just to mention in the talk. So this is some details of the meshes that we create with the previous geometries. You could see here how we have the internal wall, which was an interesting exercise to analyze something that we have in the real alveolar sacs. This is used mainly to understand some bifurcations and connections between sacs, and again, some details. And Bob with some details of the mesh, and Big Bob here that we also create all the workflow, including the mesh and the simulation. These are some numbers. And let's go to simulate. So what we solve is Navier-Stokes equation with moving walls. So we impose some movement on the surface with this arbitrary Lagrangian Eulerian formulation. So the displacement of the mesh was imposed in the surface, considering these breathing cycles as a sinusoidal cycle to represent an inhaling and exhaling process with 4-second cycle. And we create these 4 different maximum displacement that emulates different physiological conditions. So let's go with the results. These are some images of a pressure file in the 4 meshes, and you could see the average on the surfaces for the 4 different displacement, in this case for the Big Bob geometry. And all of that curves was needed for us to see if the physiology is fitted or corresponds with the real data that you could see in physiological bibliography or medicine bibliography. So for the flow rates, we compute also the same curves and compare with the flow rate that, if you consider your geometry as a dichotomical branching structure, then you could idealize that the resulting flow rate that you could have in the 22nd, 23rd generation, which is the generation where our geometry is representing, you could see a great fitting with the flow rate that we create when we move the surfaces and simulate the flow rate. This is the same for Big Bob, which is the winner. And some data, or this table is to represent the volume expansion in each case that we have simulated. So let's go with the particles. So we transport particles, not only the fluid inside the lungs, but we transport particles. Our model in this case is a one-way coupling, so in a passive way, using a Lagrangian frame of reference and considering these forces. Once we obtain acceleration, we integrate to obtain velocity and finally position to track all the trajectories of the particles, which is the real target that in many applications it's needed. For example, this is an example of that tracking. So these represent 3 cycles for the breathing process, where we are inhaling and exhaling with the 4-second period of time. So this is the second cycle, and now start with the last and third cycle. Once the particles are traveling, in this case, the colors represent the different sizes for diameters, then we obtain the final deposition maps that let me show briefly with some statistic of deposited, suspended, and exhaled particles. This is to give you an idea of the utility and which could be a proper analysis or interesting questions that offers that technology. This is the deposition map for the first mesh, the second mesh, we obtain different statistics and of course the position maps. Then we can play with the gravity, position, and so on and so forth. It's an illustrative proof of concept. And finally, for the Bob and for Big Bob, you could see a comparison as the title of my talk. But again, this is mostly just to give you an overview and an idea of the utility of this technique. And let's go with the computational resources as a part C of the conference. So these are some numbers of the cost in time and CPUs to solve the fluid flow, which is for one cycle. Where once we obtain the solution for one cycle, we frozen the field and transport particles 3 cycles. So these are the computational resources for the particle transport. And well, let's delve a little bit deeper into this issue, which is not trivial. So work is not well balanced in general due to many reasons. The partition is not perfect, or the physics or numerical method is not really heterogeneous, and so on and so forth. Remember that we are also solving different equations, Navier-Stokes or fluid flows, but also the particle transport, which has different properties. So how to parallelize the fluid flow equation is with the maximum of divide and you will work. And in this case, each of that color represents the subdomains for each CPUs. So once you divide and compute each part, you need to communicate the results and obtain a global solution. Okay, but again, remember, we need to parallelize for the transport of the particles. In this case, we use the same partition, but, well, ideally, what you have to solve is the transport of the particles of each part of the domain, and then once the particles are moving, they are migrating probably from one to the other. So at the end, how do we know we are doing well? Well, a super useful tool, it's analyze a trace. A trace enables to visualize the state of all the cores, where is what is working, what is communicating, what is happening inside the machine. And this is a typical or usual, well, this is the usual aspect of one of the traces, where each part corresponds to one of these cores. But the ideal situation is everybody working and as more efficient, better. Well, don't be so demanding. Some communication is needed, but as most are synchronized and a slight part of communication, better. So this is the usual situation. In fact, this is the real trace for this specific case, that if you filter the events that you need to analyze, looks like that. So considering our partition, this represents the graph, the communication between these different subdomains and all the CPUs that was involved in this specific case. But again, remember that particles are injected, in this case, in this slide from all the three-dimensional volume. So one of these CPU is involved in the transport. Then a good option is to share the resources. In this case, it's in the shared memory level, using this nice tool developed in BSc in another department from our colleagues. And this is the runtime dynamic load balance library that aims to gain time in the global running. So in this case, that we are transporting particles in that manner that I showed you before, one of that CPU is working, the others are just saying. So with that library, what you could share with that other CPUs, the working process, reducing the time needed. So this is what you could see in the real trace, that at the end, if you don't use the library, one of these CPUs working, the others not, different greens in that case. But if you use the DLV tool, all works and time is reduced. But in general, load imbalance is always there. Load imbalance is a serious issue when transporting particles, but can be partially fixed or solved. So as a conclusion, Big Bob was the winner. This is a novelty geometry that we would like to working and going in deep. As I told you, we are working in the construction of a most realistic volume size, but considering the same techniques. But take into account that all is with this absence of medical images, so it's not a trivial process. But it's a big step on personalized medicine. All of these kind of applications would be useful to evaluate the damage of pollution or how the virus infects and propagates, or inhaled treatments, and so on and so forth. So as I told you, we are working on the new geometries. We could simulate the fluid structure interaction. The problem is, how do you know the proper properties for the elastic tissue? But if any of you have any insights, please let me know. Improve deposition model for particles, as Silvia, I don't want to mention and do a spoiler, but we'll present later, or reproduce some pathological conditions. And finally, coupling organ and cell level, but this is the next presentation for today. Okay, thank you.